wanted to each of the rectangles, and you could find an equivalent layout that would realize that. It's been shown that every generic layout, which is a layout where no four faces share a corner and meet at a single point, is weakly area universal, meaning that you can find a weakly equivalent layout. And it's strongly area universal if and only if it is one-sided. Now, one-sided is also something that will come up in our work for aspect ratio universality. So I'll define that better later. And yeah, as you can imagine, this is very useful for cartograms and data visualization. Our contribution is the notion of aspect ratio universality and a characterization of it. So we say that a generic layout L is weakly or strongly aspect ratio universal if any assignment of aspect ratios to the rectangles can be realized by a layout weakly, strongly, or strongly equivalent to L. So it's the same idea as area universality, where you have the layout and the rectangles are all in the same positions. All of the interior line segments line up in the same ways. But now we care about aspect ratio. And this is something that can come up, for instance, in word clouds. If you imagine, if you know of a word cloud where you have a lot of words all together that represent some concept or maybe like their frequency of use. If you wanted to translate that into a different language, words would have different lengths, and therefore their bounding box would be a different aspect ratio. I haven't really defined aspect ratio. I suppose I should do that now. The aspect ratio is just the ratio between the height and the width of the rectangle. So our characterization of aspect ratio universal layouts is that a generic layout is weakly aspect ratio universal if and only if it is sliceable, and I'll get to what exactly that means momentarily. And then we have a characterization of strongly aspect ratio universal layouts, which is that if a layout is strongly aspect ratio universal, then it is also one-sided and sliceable, and its extended dual admits a unique transversal structure. Again, all of that will be coming up in the next few slides. And those are all equivalent properties. So to start with one-sided and sliceable. One-sided means that every maximal line segment in the interior of the layout is the side of a rectangle. So if we look at this rectangle here, this is actually not a one-sided layout because of this line segment here. As you can see, it has line segments dividing it on either side. And of that upper line segment, now this is a one-sided layout where every single maximal line segment, which is the line segment like expanding the full length of it, you can't stop before you get to the end of it. Every maximal line segment is the side of some rectangle. You can pick any one of them and you can find a rectangle that it is the side of. So that's one-sidedness. Sliceable layouts are ones that can be obtained through recursive subdivision of the bounding box with vertical or horizontal lines. So for instance, if we wanted to construct one, we can subdivide vertically, and then we can choose any of the rectangular sublayouts, or just any of the rectangles currently in the layout, and subdivide those. So it's just anything that can be done by recursively subdividing like this. And again, the result is that a layout is aspect ratio universal, or ARU, if and only if it is one-sided and sliceable. So both of these properties together. On transversal structures, we take the extended dual graph of a layout, and the extended dual graph is an extended form of the dual graph, as you might imagine, where we add basically virtual faces for each of the sides of the bounding box and associate those with a vertex. And then any rectangles that touch that side of the bounding box that are in contact with it, we add an edge between their corresponding vertices and the vertex of that side of the bounding box. And we get the extended dual graph. So it's we're basically just adding a 4-cycle around the outside of the dual graph. The transversal structure is a coloring and directing of this extended dual graph, where you direct all of the lines or all of the edges from the west-hand side to the east and south to north. And you also color them based on the contacts between the rectangles. So if the two rectangles are in contact with horizontally next to one another, you're going to color that blue. And if they're in contact vertically, then you're going to color that red. So our result is that the extended dual of a layout L admits a unique transversal structure if and only if L is one-sided and sliceable. And that is, again, equivalent also to aspect ratio universal, which we'll get to. Yeah, so it needs to be if it admits a unique transversal structure. So there's not more than one way to color and direct these edges. Now, it is known that for a extended dual graph with n inner vertices, and all of those can be the transversal structure for that can be transformed into any other valid transversal structure by a sequence of these flip operations, which is changing the colors of the edges on the interior of an alternating 4 cycle. So if we look at this first figure here, we've got an alternating 4 cycle on the outside, alternating colors, and we can change the color of the edge in the middle. So through a series of those flip operations, we can get from any from any valid transversal structure to any other valid transversal structure. So in order to have a unique transversal structure, it can't have any of these flips possible in it. And that turns out to be equivalent to one-sided and sliceable, because if we look at the figures here show basically sort of cases that are always going to have one of these flips. And the top one is not one-sided, and the bottom example is not sliceable. And it turns out if it's not one-sided or sliceable, it will always contain something like one of these and therefore contain a flip. So that's why these 3 properties are all equivalent. Well, I guess the last one to show is that these actually are equivalent to aspect ratio universality, which again is allowing us to assign an aspect ratio to each of the rectangles in the layout. So no matter what you assign to them, it's realizable in a actual way that fits. So it's pretty easy to show one direction of this, but it's an if and only if statement, so the other way is a bit harder. It's easy to show that if it's sliceable, if the layout's sliceable, it's weakly aspect ratio universal. And that just comes from, let's think about just a simple case with 2 rectangles next to one another. We can assign any aspect ratio. So let's say we make it really flat like this. We can just scale it up. Aspect ratio is scale invariant. So as long as we can scale it up and just kind of fit it along that slice that was dividing them, it's always going to fit. And it follows through induction that any aspect ratio assignment is realizable, because we can go down to the smallest component and for just 2 rectangles next to one another, assign any aspect ratio to those. We've already shown that that fits. And then whatever their union is, that will itself have some aspect ratio, which we will then be able to join up with whatever the next slice is. So it just continues all the way up. And so if it's sliceable, then it's weakly aspect ratio universal. The one-sidedness for strong aspect ratio or universality comes in when you have both sides further subdivided, because we can't guarantee that any lines that touch the slice, any slices that are adjacent to it, we can't guarantee how they're going to line up. So like these 2 cases are, we just don't know which one we're going to get. Enforcing one-sidedness, though, will guarantee that one side of any slice is itself a rectangle and therefore not subdivided. And therefore you don't have to worry about how things line up at all. So once it's sliceable and one-sided, you just get strong aspect ratio universality. And oh yeah, we should get rid of those extra slices there. And this, you could further subdivide the other side, but you do have to leave that like rectangle gap there. And so yeah, so showing one direction of the argument is fairly easy. The other direction is a lot harder. So the converses of each of these, showing that if something is aspect ratio universal, then it must be sliceable and one-sided. The main idea behind how we did that is with these prototype layouts. So we showed that every sliceable layout, every layout which is not one-sided can be reduced in some sense to one of these layouts A through D. And these are layouts where you cannot assign aspect ratios. So for instance, getting from A to B is just changing the aspect ratios, but you can see that it makes it so that it's no longer, that it's not strongly equivalent. It is weakly equivalent, but as far as strongly equivalent, with that these 2 prototype layouts do not work, because if you assign the exact aspect ratios from B to the one in A, you get a different layout. So it's pretty easy to show that for the ones that are not one-sided, because you can basically just find this exact layout in the layout somewhere and assign the aspect ratios. And it may be further subdivided, but it's a pretty simple way to still get more or less this exact thing. With the ones that are not sliceable, it's a bit harder because we end up with the same sort of idea. If it's not sliceable, it's going to contain this kind of prototype layout somewhere in it. And this has what we call a central windmill. And it's been proven that every non-sliceable layout has a windmill like this somewhere in it, which is these four lines that we've highlighted in red here. And so in order to get something that looks like this prototype, which we can show is not aspect ratio universal, we have to subdivide the layout itself into 4 quadrants that look roughly like that. And the exact way of doing that is somewhat difficult because we can't, obviously, like the layout isn't just going to have full rectangles in those quadrants. So what we tried to do is partition the rectangles into 4 different sets and show that each of these sets, the union of them, we can assign aspect ratios in some way that will force it to be not realizable, force the whole union of them to behave in a way that's similar to the prototype. So that's the main idea behind this. Most of the difficulty here was in actually finding the paths because we had to make sure that they don't intersect each other in order to get 4 unique or 4 separate and only 4 separate quadrants. And we had to ensure that they each reach the different sides of the bounding box. Once you do that, though, you can assign aspect ratios to say, like, okay, the whole union of this must have a bounding box that's at least has aspect ratio 3 or something along those lines. That's the general idea. I'm not going into it in too much detail because it is fairly in depth. But yeah. The other thing we did was found a quadratic time algorithm for identifying the dual graphs of aspect ratio universal layouts. So it is possible to decide whether any graph is a proper graph, which is to say a dual graph to some layout. It's possible to decide that in linear time. But as of yet, there is no polynomial time algorithm known for identifying the duals of sliceable layouts. So it's a little bit harder to identify properties just from the dual graph. So we included an order n² time algorithm for deciding whether a given graph is the dual of a one-sided and sliceable or aspect ratio universal layout. And in order to do that, we made heavy use of cut vertices and 2 cuts to determine the properties of any layouts that you get out of this graph. And yeah, so an open problem is whether this runtime can be improved. We also showed that the duals of one-sided sliceable layouts have vertex cuts of size at most 3. So it's possible that that fact could be used. The way the algorithm currently works is if it doesn't identify any cut vertices or 2 cuts, it kind of just does a brute force search at the start. So it's possible that we could use the 3 cuts to find a faster algorithm and perhaps even reduce this to linear time. But yeah, that's future work. Anyway, that's my presentation, and thank you.
Thank you very much for your presentation. Are there any questions for Andrew? I've got one. You said that maybe you can improve the time complexity of your algorithm using 3 cuts. Have you already tried that, or is it just a conjecture, intuition?
We did, yeah. So we did start working on it, and we have like a basic idea, and we basically just didn't have time to like fully write it up and make sure it actually worked. But it seems like there is probably a way to do it just based on what we did so far.
That makes sense. Yeah. Okay. Thank you very much. Are there other questions for Andrew? If none, then we move to the next talk of this session, which is morphing 3 drawings in small 3D grid.
Right, thank you.
And Alexandra Istomina is giving the talk. Alexandra, the stage is yours.
Yes. Hi. Can you see my screen?
I can see your screen, and I can also hear you.
Yeah. Hi. My name is Alexandra Istomin, and I'm going to present our joint paper with Elena Arseneva and Rahul Gangopadhyay, morphing tree drawings in a small 3D grid. So we will be working with planar straight line drawings of trees on a grid of polynomial size in 2-dimensional and 3-dimensional space. The example of such drawing you can see in the right. And we will want to transform between these drawings through something named the morphing process. Our morphing will consist of several morphing steps. And in each morphing step, each vertex of a tree that we have is assigned some vector of movement. They can be different for different vertices. And throughout the morphing step, each vertex is moving along its vector of movement with one speed. So here in the picture, they're shown, the vectors are shown in red, and these are two morphing steps when we move our vertices. So what we want to maintain planarity throughout the whole process. So it can be not possible to morph from one drawing to another in just one morphing step. We may need several. The question is, how many can we need? It is known that for two plane drawings of one graph, there is a linear time algorithm in terms of morphing steps, and this boundary is asymptotically optimal. But in that algorithm, there is no bound on the grid where the vertices can lie, or which is the same, there is no bound on the resolution that the graph may have in between. So another question that was addressed, that if we require that vertices of the graph after every performance of morphing step lie on the lattice points of the grid of the polynomial size, how much steps should we need? And for the trees, it has been found an algorithm in linear number of morphing steps. And another way to ask a question is how fast can we morph between two plane drawings of trees if in between we can use 3D, so the third dimension. And without the requirement on the size of the grid, there is a logarithmic algorithm. And in our paper, we wanted to combine these two approaches. So we want to morph between two plane drawings of trees through 3D, but maintaining some bound on the grid. So we have created two algorithms that are linear in number of morphing steps, and they are not better than the best algorithm known in plane, but their combination is already sublinear. And in both algorithms, the basic idea is to learn to morph from the given drawing to some canonical one that is shown in the center here. And if we can morph from the given drawing to the canonical one, then we can morph between any two given drawings just through this one, and plane the morph from the second one to the canonical backwards. We suppose here that the given plane drawings align in the plane z equals 0. And about the canonical drawing, I will talk later a bit. So the first algorithm transforms our tree from the plane drawing to a canonical one, part by part. And here the parts are sets of edges of equal depth. So in both drawings, we choose a vertex to be a root of our tree. And now we have a rooted tree, and we can define the depth of each vertex in it, and so the depth of the edge. So we split the edges into sets with equal depth, and starting to canonizing these sets one by one from the deepest one to the root. For every edge set, we spend at most logarithmic number of morphing steps. So if the depth of the tree is linear, our algorithm is not better than the best algorithm that is known for plane. In the second algorithm, we split the edges of our tree in a different way. we split it into root to leaf paths. And then we transform this path to a canonical way, one by one. In the second algorithm, we spend only a constant number of morphing steps for each path. The same drawback is that the number of paths in the path decomposition can be linear. So here we also do not do better than the best algorithm known for plane. But their combination can give us sublinear algorithm. We apply first algorithm for some subtrees of our tree and the second algorithm for some paths. So in the combination, these subtrees and these paths give us our initial tree. Now let us define the canonical drawing. It is defined through rooted path width, or RPW for short. Rooted path width is defined for rooted tree. So suppose we have the rooted tree that is in the left. So for the leaves of the tree, rooted path width is equal to 1. And then for every internal vertex, we look onto RPW of its children, and more specifically on the children with the maximal RPW. Here, for example, the vertex has children with 2 maximal RPW. These are both ones. And if there is more than one child with this maximal RPW, this internal vertex has our RPW of this maximal plus 1. If there is only one vertex with this maximal RPW, for example, in the left, so for the internal vertex, RPW is equal to this maximal. Based on RPW, we can create a heavy path decomposition of the tree. For every internal vertex, the heavy edge goes from this vertex to one of the heaviest in terms of RPW of its children. So we now have several heavy edges and several light edges in the tree. And here we'll also suppose that if the vertex doesn't have a heavy edge adjacent to it, that it creates like a heavy path of its own, consisting just of one vertex. This path decomposition is not very good for us because we want every edge lie in some path. So we transform it a bit, and to every path that we have, we add an edge that is right above it to this path. That's how we go to new heavy path decomposition, and based on it, we are drawing a canonical drawing of the graph. So the canonical drawing will lie in the first quadrant of XZ plane, going through the root vertex, and the heavy paths will be drawn vertical, except maybe for one per stage of every path. The good properties of this drawing is that the height has the maximal difference between the coordinates of the vertices are equal to the number of vertices in the tree, and the width is the maximal distance in x coordinate is logarithmic from the number of vertices in the tree. So here I want to present a sketch of the first algorithm that lifts our tree by the sets of edges of equal depth. And first of all, the first step that we do, we multiply the coordinates of our given drawing by some big constant s to avoid intersections in the next steps. So we somehow stretch the given drawing in s times. After that, here on the left, you can see an example of such tree. We divide the edges onto the sets of equal depth. They're shown in different colors. And then we are starting to apply lift procedure to each edge set from the deepest one to the highest. So first of all, we apply lift procedure to the violet edges, and we go to the center of picture. What we suppose? We suppose that all the vertices that lie in the non-processed edge sets, we do not move them. They lie in the same place in this horizontal plane where they were. And the edges to which we have applied lift procedure, they are in canonical way with this subtree that they have. So now I want to describe the application of lift procedure to the light green edges and the steps that it consists of. And I will be focusing only one vertex V, root vertices are the vertices of green edges that are closest to the root. There can be several of them, but I will focus only on one because the process will be the same for any of them. So the simplified view that we get is on the right. There is one root vertex and several of its neighbors with their lifted subtrees. The first step that we do is we shrink this picture. So we move U vertices towards V vertices. All the vectors of movement are horizontal, and for each subtree of U vertex that is lying in this violet bounding box vertical, they have the same vector of movement as the U vertex. After that, we want to create the height of U vertices, and we move them up. So here, all vectors of movement are vertical, but they are different, and they depend on the height of U vertices in the canonical drawing of the subtree of V. After that, we want to place the subtrees of U vertices in the same vertical half plane that contains the corresponding edge VU. So we look at the yellow vertical planes. There is exactly one for each green edge that contains it. And we want to map the drawing of the subtree of the corresponding U vertex to this plane. And the next step is another shrinking move. And here, exactly as in the step 1, we just horizontally move U vertices along with their lifted subtree towards the pole containing the U vertex. Step 5 is the most complex one. It consists of several morphing steps. And so after the step 4, we have a picture in the left, so vertex V and several vertical half planes around it, which we want to transform to one plane containing all the edges and all the subtrees. So we split the planes that we have in pairs of neighboring ones, and in each pair we map one plane, one half plane to another. So we're colliding the planes together. After one morphing step, we decrease our number of half planes twice. So we may need up to a logarithmic number of such steps to collide them all together in one half plane and place it in XZ plane from vertex V. So here a logarithm is from the number of, on the maximum degree of the vertex can have in a graph. So here is the logarithm of degree of vertex V. The second algorithm is pretty much the same. So the first step is also stretching. And after that, the application of the lift procedure to the paths one by one. It consists of 13 steps. And here I'll just say that first 2 steps are preparation steps. So we also do them to avoid the intersections later. Steps from 3 to 6 are devoted to placing the coordinates of the paths. In the canonical form from like third to the last, they move into their canonical positions with respect to the second vertex of the path. After that, from 7 to 9, we place lifted subtrees of our internal vertices of the path to their canonical positions. After that, here we get the tree in canonical form for the second vertex of the path. And after that, in the last 4 steps, we place this second vertex in canonical position with respect to the first vertex. Now let us see how do we combine these algorithms. So suppose we have a tree. We want to form some set of long paths to which we will apply the second algorithm. So we take the longest root to leaf path of the tree, put it into the set of long t if it has the length at least square root of n. Then we delete the edges of this path, and our graph may become disconnected, so there is a forest now. And we repeat the process, so we take the longest root to leaf path that we have, check if it has the length at least square root of n, and then add it into a set of long t. After that, we will stop sometime, and we will get a set of short T, which is the forest where each tree has depth at most square root of n. And to this forest, we will apply the first algorithm. And as the depth is not very big, we'll spend only sublinear number of morphing steps to leave this tree. And after that, we apply the second algorithm for a set of long paths. And as we can't have many paths of length at least square root of n, we spend also sublinear number of morphing steps for this part. And the total number of steps in the combination is sublinear. So we have created two algorithms for 3D morphing between two planar drawings in tree on a grid of polynomial size. In the first one, we are lifting three set by set of edges, so we call that, spending this kind of steps for each edge set. And the total number of steps is like that. Note that for trees with bounded degree, it is linear in number of morphing steps in the worst case. And in the second algorithm, we forming canonical drawing path by path, spending only a constant number of steps for each path lifting. And the second algorithm complexity is linear from number of paths in the chosen path decomposition. Here you can know that path decomposition you can choose on your own. So the only requirement is that every path should be a part of root to leaf path, and every edge should be covered by some path. The combination of this algorithm give us a first sublinear algorithm to our knowledge for this problem. And obvious subsequent question is, can we do faster than that? Because we know that without the restriction on the size of the grid, we can just transform between two drawings in logarithmic number of morphing steps. Maybe we can do faster than square root of n here. The dual question is there some lower bound on the number of steps that we need? And this question is interesting in both cases. If we add or if we do not add the restriction of the polynomial resolution, or which is the same on the polynomial size of the grid. Or another approach can be to discover the algorithms for other graph classes, for example, cactus trees or autoplanar graphs, or graphs with bounded tree width. All this will be interesting. Thank you for your attention. I will be glad to answer questions if you have any.
Thank you very much, Alexandra. Are there questions for Alexandra? I have one. What is your feeling about the lower bound? So do you feel that the lower bound is much lower?
Oh,
do you have any feeling about it?
Really, I don't know. It's just first I tried to create an algorithm with just a logarithmic number of steps as it was for unrestriction case. And also it is known that if we allow to use higher dimension than third, like fourth and so on, we can just do it in 2 steps. So for that case, it is just constant number of steps is null, and it is just no lower bound needed. And here, I don't know, but logarithmic bound looks somehow promising.
Okay, thank you very much. Is what I figured that too. Okay. Okay, thanks. Thank you very much. Are there other questions for Alexandra? If none, then we can move on to the third talk of the session, which is STEAM table, an area proportional visualization for tables with flowing streams, by Jared Espanant and Debayotti Mondal, and Jared is giving the talk.
Yes, hi. I'll share my screen. I assume that you guys can hear me well.
We can hear you well, yes.
Okay, that's good. And the screen is visible?
Yes, please. Yeah.
Okay. All right. So hi, as mentioned, my name is Jared. Thank you all for coming to listen. It means a lot to me that I'm able to be here. Today I'll be presenting on the paper done by myself and Dr. Mandal, which is the stream table and area proportional visualization for tables with flowing streams. First, I want to do a brief introduction on various visualization tools that we have taken some inspiration from. These are primarily the Table Cartogram and the stream graph. The stream graph is a way to visualize the amount of information over some variable of time. So if you draw your attention here to the top left diagram, this is the popularity of various musicians over time displayed as a stream graph. Here, for example, we can see that Green Day is quite popular in the middle of the graph, and then it dwindles off over time. Conversely, we have another visualization tool, the Table Cartogram. Here we are given some sort of input table. This could be, say, sizes of elements in the periodic table or a map or something, but the basic idea is we then want to scale the value inside of each cell in proportion to its relation with every other value, so that larger values, such as this 9 down here, become much larger in the visualization, and much smaller values like the 3 become much smaller. This gives us the benefit of understanding both the relationships and adjacencies between these various elements, as well as their relative magnitude. There we go. So that is the base motivation for the stream table. We wanted to try and visualize tabular data while taking the best components of both of these techniques. So sometimes in the table cartogram, you have to sacrifice a certain level of visual clarity to maintain adjacencies, to have a more compact visualization. And with the stream graph, you are able to see the progression of data over time in a very dynamic and interesting way. So we decided to take a more theoretical look at the stream table, which aims to merge the best of these techniques into a new visualization tool. Here is a kind of proof of concept of what it might look like here with some aesthetic smoothing. We have here various years for the Olympics and the total medals, and using this, we can extract certain elements of data. For one, we can see that the total amount of medals distributed has increased with each year, or at least attained by the set of countries selected here. We can identify other trends, such as the increase of medal acquisition for countries like Canada and the seeming decrease for other ones, such as Finland. So more formally, a stream table takes an R by C table T of positive non-zero values, and we want to perform a new partition with a very specific rule. We want to make sure that all of the horizontal lines are axis aligned. So note that we are restricting ourselves from the table cartogram by allowing or enforcing each row to share horizontal lines above and below. Once we have created our horizontal partitions, we can then partition them vertically, and that will give us our resulting stream table. Here we can see that the two additional restrictions that are required are that we want the left side aligned to give it a good aspect ratio as with the right. And finally, we want to make sure that the relative size of each cell is proportional to the size of the initial data. That way we can get something useful out of it. The two metrics that we are primarily looking to measure the quality of a stream table are through splits and excess area. Splits is the idea of sometimes we have to sacrifice the consistency of some of these vertical streams, say this purple one here. So we are having a more compressed stream table at the price of adding in these splits at these three different locations. So we can talk about trying to minimize the number of splits in a stream graph. Instead, we can take a different approach where we wish to minimize the amount of excess area. So here we want to make sure that our streams are connected no matter what, but in that case, we have to introduce additional excess area to give it the proper flow we are looking for. Our goal here is to explore the stream table from a primarily theoretical perspective. We're looking at this from two main areas. Firstly, a stream table with no split and minimizing the excess area. So this is, in essence, a kind of optimization problem. And we are also looking to fix the row ordering. Conversely, for problem 2, we are looking to see if permuting the rows can give us a more optimal solution. Sometimes the data that you have doesn't necessarily need to be ordered on a per row basis. And so perhaps by rearranging the rows, we can come up with a more compact solution. For problem 1, the first solution here would be a greedy one. This is kind of follows from the intuition of just trying to compress the excess area as much as we can. So we can construct this in a repetitive process. First, we take the leftmost column and we make sure its left side is aligned. And then for each intermittent column, we basically want to push all of these cells as far to the left as possible without breaking the streams. And then finally, we want to hold the same rule for the rightmost column while keeping in mind that we are still looking to have a nice rectangular output. So this process as a whole takes big O RC time, which is good, but this is all under the condition that these row heights are fixed. They are non-variable. And so we have to come up with a different solution if we wish to try and fix that. Here, an alternative idea is to use a system of equations. Here, we can define our problem as a system of linear equations for 1. Once again, the constraints that we define are in part based on the definitions that we are working with, which would be left and right properly aligned, the size of each cell proportional to the size of the data it represents, and ensuring that our streams do not break. Once again, if we do this linear, however, we are fixing the row heights. If we choose instead to keep the row heights variable as well, then we are left with a quadratically constrained system, which is not nearly as efficient. However, there is one workaround that can be introduced, and this is what we call a post-height reduction. The idea here is that when we are implementing these algorithms with a certain fixed height, we can retroactively try and decrease the height to shrink out some of this excess area. So we can select one of these excess area cells and keeping all others equal, reduce the row height, and then the only thing then that can give is the excess area. That can be expressed as this set of equations down here, and we are finding this intersection point. Lastly, if we wish to see if we can restrict our row heights to integers, perhaps then we variable them. This is also NP hard. If we're given a total height and we are restricting our row heights to be integers, deciding what integers for each row height to be is in itself NP hard. We are showing this by transforming the maximum clique problem. There will be a couple NP hard proofs along these lines, and they all follow the general flow. We are basically looking to express the vertices as the rows and the edges as the columns. And then we define these large initial cells based on the relationship that a vertex has to that respective edge. And then we also have these thicker columns, which are precisely chosen so that the size of one column does not affect a shift of the other. It allows us to inspect each column individually and avoid a lot of the mess. So here, what we're looking to do is we need to choose the additional integer heights for various rows such that if the overall length of the table, if the overall length of the table is less than a given threshold, then we will have solved the clique problem. Thus, it is NP hard. Moving on to problem 2, if we are looking to try and permute the rows to obtain a more optimal solution, both permuting rows to minimize the number of splits or the amount of excess area, both are NP hard. Firstly here, if we are looking at minimizing the splits, we can show that it is NP-hard by transforming the Hamiltonian path problem. Once again, we are taking the concept of applying vertices to the rows and edges to the columns, and then we carefully define the contents of each of these larger columns based on the relationship that the vertex has to the edge. And then we can subdivide it into the smaller columns. Once again, if we can order the rows such that it provides a Hamiltonian path, then we will have found the minimum number of splits. So this is also NP-hard. Lastly, if we are looking to show a row permutation for minimum excess area is NP-hard, we are going to use the betweenness problem for this. This is a known NP-hard problem. The idea is you have an input of triples over some alphabet. Here I'm just using the integers, and we want to choose the integers in such an arrangement that for any triple, I will still find that the output is in between. So for example, I can see for 1, 4, 5, I see that 4 is still between 1 and 5. For 2, 1, 3, I see that 1 is still between 2 and 3. Here a non-solution is just ordering them from lowest to highest. The way we can go about this is we can define the rows to be the total amount of numbers that we are working with, and then each column based on the input triples. And then again, it's the same idea here. We are having these thin columns to restrict their interaction with one another, as well as then defining the contents of these larger columns and the cells based on these relationships. If you can find a proper arrangement, then you can also show the resulting permutation for rows is NP-hard. In conclusion, stream tables offer, I think, a very interesting visual tool. You're able to still compare things row by row, which is something that might be lost in certain table cartograms. And you also get then the measure of the stream graphs simultaneously. The two primary open problems here that we are looking at, most importantly, is our initial statement for problem 1. All provided solutions are assuming that we're having a fixed height. To have a general efficient polynomial time solution is not yet known if that is possible, and that's currently what we are working to figure out, because that would obviously be able to give us the strongest solution. Additionally, there is the potential of permuting the columns. We might be able to find a benefit in the same way that permuting the rows allows us to have. And that's a wrap.
Thank you very much for the presentation. Are there questions? I have one. In your model, you basically focus on a single table. This makes me think about hybrid visualizations of clustered graph, where clusters are represented as matrices, and maybe that the vertices have some weights, and you may want to use your representation for a different visualization of these matrices. Have you ever considered this direction?
No, that's a very interesting thing that you brought up. The primary focus was purely trying to get the efficiency results of developing one of these stream tables. So seeing how fast we can develop it and with what conditions, looking more to the application side or how it can be used in tandem with other tools hasn't been fully explored.
Okay, so are there other questions? Okay, if not, I would like to, this is the end of this session. We have 5 minutes. We are ahead of schedule. We have 5 more minutes to relax before the next, the invited talk. I would like to thank all the speakers of the session for their talks, for their nice presentations. And I hope you will enjoy the rest of the conference. Thank you very much. Thanks.
Okay, thanks to Mr. Sim Nakano and Giuseppe Leotta as a chair at the contributor talk 1 and 2. Now we are going to the next agenda. The next agenda is invited talk 1 and contributor talk session 3. The topic is computational geometry. In this session will be led by Prof. Sayyidul Rahman and Mrs. Minatide as a chair. Okay, for the first session, for Prof. Sayyidul Rahman, time is yours.
Okay, actually we will start at the right time, that is 12:30, 11 in Indonesian time. What will be that? So we'll start at 13:30. So we'll wait a few minutes. I hope Professor Tj Ana Kalamundi is here.
Yes, I'm here. Can you hear me?
Yes, yeah? I can hear. So you may test your slide or share your slide.
Yeah, I can. Shall I do immediately, right?
Yes, you may check.
Okay, do you see them?
Yes, I can see the slides. So we need to wait a few minutes, say 3 minutes.
Sure, fine. So how is it going, the conference? Are you enjoying?
Yes, the inaugural session was very nice. And after that, we had 2 sessions and all the presenters were present. And every talk was very attractive and enjoyable.
So are there many people there?
In online, around 40 people are participating.
Sorry, how many?
In online, around 40 people.
Okay. And what about in place?
In place, actually, there are people, participants from Indonesia are participating.
Okay. Okay.
Mandi dulu, makan dulu, nak. Sholat belum lagi. Apa tuh? Sudah apa? Throwing, chasing, kicking, catching. Apa arti? Kicking kali. Hah? Throwing, chasing, kicking, catching. Apa bedanya tuh?
Chasing itu apa namanya? Mengambil.
Okay, let us start. Okay. Dear participants of WALCOM 2022, welcome you all to the invited talk session 1. In this session, we have a very distinguished speaker, Professor Tj Ana Kalamundi. Let me briefly introduce Professor Kalamundi. Professor Tj Ana Kalamundi graduated in mathematics in 1992 and received PhD degree in computer science in 1997. She is currently a professor in the Department of Computer Science, Sapienza University of Rome. She was president of the Italian chapter of European Association of Theoretical Computer Science for a long time, from 2011 to 2017. His research interests cover all the applications of graph algorithms with a special focus on problems arising from biology and medicine and from mobile sensor networks. Professor Kalamundi was in the editorial board of Theoretical Computer Science and also worked in several program committee members of several conferences. He has several awards and achievements in her record. She received Best Paper Award at ICNP 2009 for the paper Autonomous Deployment of Heterogeneous Mobile Sensors. She also the steering committee member of SIAC, the International Conference of Algorithms and Complexity. She was an invited panelist in the roundtable of Italian Theoretical Computer Science at ICTCS, and she also received award Sapienza Ricerca in 2010 for the research on the autonomous deployment of mobile sensors. Now, I request Professor Tj Ana Kalamundi to present her talk on some problems related to space of optimal tree reconciliations. Welcome, Professor Tj Ana.
Good morning, and thank you, Saidur, for inviting me to give this talk and for your nice presentation. So today I will speak about some problems related to the space of optimal tree reconciliation. I choose not to enter into details, of course, but to give just an overview of the problems of some known solution and some interesting open problems. And I suggest the interested people to refer to the paper on the proceedings for the details and full references. So in order to speak about reconciliation, we need to speak about coevolution. This is a concept introduced by Darwin in 1859, although he never used this name. And it was introduced for the because he understood that something had to happen somehow in nature. For instance, he discovered that this flower, and he thought that its dust was so deep that there must exist an insect able to catch it. Now we can see in the picture this insect exists, and it has been discovered later, and this is the reason why in the scientific name there is this word predicta, because Darwin thought that it had to exist, but I mean, he never could see it. And so this is one example in which we see that there are two beings that evolve together somehow. coevolution is wider than what it seems, because many situations like these ones can be considered as co-evolving systems. Just an example is the case in which we have a host and a parasite that lives on this host, but there are some other cases. And what is nice is that all of them can be described more or less with the same model. And this is the reason why I will speak along all the talk with the words concerning host and parasites, because somehow they are the most intuitive. But of course, you can substitute these words with those relative to the other systems. Now let's look at the ingredients of this receipt somehow. So we have two phylogenetic tree. One is concerns the host and is called H, and another one is concerned the parasite, and so it's called P. And what is a phylogenetic tree? It's a tree in which on the leaves we have the beings that are living today, while there are some ancient nodes whenever we discover that there is, of course, a phylogenetic relation between these beings. So when we go from the leaves to the root, we go back in the time. And moreover, the last things we need is a leaf mapping function, phi, connecting the leaves of one tree with the leaves of the other tree. And the meanings is quite obvious. We have a connection between a parasite, a leaf parasite with a leaf, host leaf, if and only if there is that parasite lives on the corresponding host. Now let me observe very briefly that this is not a completely realistic model, because there are many examples. For instance, the fruit fly, that is a parasite that does not affect a single host, but it can go on many hosts. But this is the model, and we will speak about this problem later. So now we are ready to define a reconciliation. Now, very informally, a reconciliation is a mapping from the nodes of the parasite tree to the nodes of the host tree, such that the leaf mapping function is respected. So somehow what we have to do is to take these two trees and let them correspond on the leaves, and then to map all the rest of the leaves of the nodes so that they are mapped one onto the other one. And in such a context, what we can have is that 4 events can happen. The most desirable is this one. It is called co-speciation, in which we have that when the host, so let me say first that in this drawing, the pipe-shaped tree is the host tree, while the dotted one is the parasite. And you can see this is just a representation to highlight the fact that we are mapping the parasite tree onto the host one. And so the first event that can happen is the most desirable one, and it is this one, the co-speciation, in which we have that whenever the host speciates, also the parasite does the same. on the contrary, we have these two events, duplication and loss, in which only one of the two trees speciates, while the other one does not. And finally, we have the fourth events is the host switch, also called gene transfer, but we will call it host switch, that usually happens when something external happens. For instance, if the host makes a migration and moves to another place where to live, then probably the parasites that live upon it will contaminate also other hosts, new hosts that are not exactly descendant of the first host. And so this kind of jump from a host to another one is called host switch. And this also can happen. So now the cophylogeny reconstruction problem consists in determine reconciliation given these two trees, H and P, and the leaf mapping function, phi. And now, since there are really many reconciliation given these three objects, then we do not look for any kind of solution, but we are looking for the optimal solution. And which can be considered optimal? Well, we can assign a cost to every one of the four types of events, and then we will minimize the total cost. This is based on what is called usually the parsimony principle that has been intensely discussed in evolutionary biology at the end of last century, and assume that somehow in nature things behave in the simplest or most economical way. For example, the fewest changes in every trait occur over evolutionary history. So now we are ready to describe which will be the problem I will describe you. So almost all of them start from the fact that biologists would like to see all possible reconciliation in order to understand which ones are biological feasible, which ones are not. And for instance, if they want to understand whether two beings have had a coevolution or not, they would like to look at this reconciliation. And so the first problem we want to speak about is the problem of enumerating all the optimal reconciliation. Of course, in order to let them see, we have to produce these solutions. Then the second thing is that the number of optimal reconciliation grows very fast, even when the trees are relatively small. And in fact, usually their number is exponential in the size of the trees. And it turns out that the size of the trees can be even huge. And so another problem is that we have to reduce the cardinality of the set of optimal reconciliation to be shown to biologists. We cannot imagine to show them millions of reconciliation for a single pair of trees. And third, of course, after that, we decided which reconciliation to show. We would like to visualize a given reconciliation in a nice and clear way. Last problem I would like to describe you is slightly different from these first three, and it starts from the idea that especially in the context of gene and species, not as much when we speak about host and parasites, we have that, unfortunately, the modern method for reconstructing phylogenetic trees produces trees that are usually unrooted. But we would like to root them, and so I would like to show you how to exploit reconciliation in order to transform an unrooted tree into a rooted one. And this is the plan of what I would like to speak you about. So let's approach the first problem. We want to understand how we can enumerate all possible reconciliation. So first of all, observe that finding a single reconciliation can be done in polynomial time. But unfortunately, some situations, like the ones on the right side of the slides, produce something that is unfeasible from the biological point of view. This is the case in which some ancestor relations given by the parasite tree are not preserved by the reconciliation. And this is called time inconsistent reconciliation. Now, if we want to look only to time consistent reconciliation that are somehow biological feasible, like the left side one, then the problems turns out to be MP-hard. And but we know that a single reconciliation is not enough, because we want efficient enumeration algorithm for the reconciliation problem. And why this? Because of course, even if we guarantee the time consistency, then different optimal reconciliation can exist. And though these reconciliation are all optimal and hence have all the same minimum total cost, that they can be quite different in terms of the mapping function or even of the number of events. And so to enumerate reconciliations in a reasonable time, we necessarily need to drop time consistence constraints. And in this case, we know that the problem can be solved efficiently. And how is it possible to do? We can do it exploiting dynamic programming algorithm. There are in the literature many algorithms and tools, but all of them are based more or less on the same approach. And that is the following. So every internal node of the parasite tree contributes to the total cost of the reconciliation only with its own mappings and with the mappings of its two children. And so on the basis of these, of course, we can produce a dynamic programming matrix in which whose size is, of course, the number of nodes of the parasite tree times number of nodes of the host tree. And what we do is to start from the leaves, and in every cell of the matrix that corresponds to a possible association parasite-host, we will put the necessary information that we need to understand which is the cost of that part of the tree if that parasite would be associated with that host. And we store in that cell all the necessary stuff in order to recognize then which is the correct reconciliation. After that, what we can do is to fill all the matrix, and of course the optimal solution will be in corresponding of the mapping of the root of P. So we will look at the row where there are all the possibilities for the root to be mapped, and we will pick the minimum one. And what we can do is to exploit the pointers that we have saved on the cell to traverse the matrix and get the solutions. Of course, in this way, we get only one of the solution, but after that, we can again exploit the matrix and go back through it. And in polynomial delay, we can get an enumeration algorithm that is able to modify the first given reconciliation in order to produce all the other ones. And just an intuition why the problem of determining only time-consistent reconciliation is somehow requires a lot of time is that, of course, what we have is that we will produce the first reconciliation and we don't know whether it is time consistent or not. But in polynomial time, we can realize if it is or not. But if it is not, we have to produce another one and so on and so forth. And the number of reconciliation can be exponential. And so who knows how many times it will take to find the first one time consistent reconciliation, okay? This is just a very brief overview about this problem, but there are, of course, very many interesting open problems that remain to be addressed. The first ones concern the fact that, as I told you at the beginning, this model we are considering is not completely realistic. And so we would like to find some more realistic models. First of all, what we know is that we assumed in what I told you that phylogenetic trees are without errors, but in fact, they can be affected by errors because of course we have no we cannot be sure that our phylogenetic trees are correct. So what if we have some degrees of uncertainty in these trees? And the other point is what I told you also at the beginning, the fact that in nature, in fact, phi is the leaf mapping function is not a function. So we would like to try to model in a best way the fact that for every parasite, we can have multiple hosts where it can go and produce a different model in order to determine reconciliation in these new settings. And from the other side, what we can do is to consider some special cases. Indeed, we said that to determine time-consistent optimal reconciliation is NP hard in general. But what about if we add some constraint? Is it still NP hard? Well, there are some preliminary results. For instance, one stating that if we reduce the dimension of the host switches, so the distance on the tree of the two extremes of the host switches, the jumps of the parasites, if they are short enough, then the problem can be solved in polynomial time. In particular, in this paper, is proved that if the distance is 2, so if the host switch happen between siblings, then the problem turns out to be polynomial. And another case in which we can prove that the problem is polynomial is when the tree structures is very special. In particular, in this paper, we prove that it is polynomial if the tree has a caterpillar structure. But of course, in both cases, there is a lot of work to do because we don't know anything if the host switch is slightly longer and if the trees have a shape that is different from the caterpillar one. Okay, so let's go to the second problem. I would like to show you what we can do in order to reduce the cardinality of this possibly very, very large set of optimal reconciliation. So in the literature, there are essentially two approaches. The first one consists in giving a definition of similar reconciliation and to output a single reconciliation instead of all those that are close enough to it. So this is the idea. And this approach works as well. As an example, let's consider the similarity measure as the smallest number of elementary operation needed to change one reconciliation into. So let's take these two reconciliation. Again, we have that the gray tube shape, the tree is the host tree, while the black one is the parasite. And here you have two reconciliation. Now you can see here that they are very similar because the only difference is that this black node here is mapped onto this node, while on the right you have that this node simply goes down. So if we consider as an elementary operation the fact of moving down one node, a black node towards the bottom, then these two reconciliation are at distance 1. And so we can consider them very similar. Unfortunately, we can, of course, extend this situation, and instead of a single node here, we could lengthen this path in a very long path, but still it doesn't change much if we take this node and moves many steps towards the leaves. Nevertheless, if the path is k step long, then now the distance between the two reconciliation can be arbitrarily large, k exactly. And so these two reconciliation will not be considered similar anymore, while they still are, in fact. So a second approach has been proposed in the literature. It is based on the definition of equivalent classes that group reconciliations that can be considered as equivalent from a biological point of view, and then you will output a single solution for every class in the quotient set. And again, I would like to show you an example just to let you taste the flavor of this approach. In this example, we have that two reconciliation are equivalent if and only if they have the same even vector. Now, what is even vector? It's very simple. You will remember I showed you before the 4 possible events that could happen in the reconciliations, and for each of them we can decide, we can simply count how many such events will happen in that reconciliation. And so I will have 4 values corresponds to the events, and this is the event vector. And we will say that if two reconciliation has ordinately the same number of events, then they are equivalent. Okay. Now, a positive side of this definition is that the number of different event vector is for sure polynomial. And so with this approach, we are passing from a possibly exponential number of reconciliation to a certainly polynomial number. Moreover, the set of event vector classes provides a first information about the evolutionary history of the host and their parasites. Indeed, a high number of co-speciation, for instance, indicate that host and parasite really evolved together, while a high number of host switches indicates that the parasites were able to infect different host species. Nevertheless, the problem of this approach, of this example, in fact, is that reconciliation with the same event vector may be even very different. And the drawing here on these slides is just an example. They have the same event vector, but as you can see, they have nothing to do one with the other ones. They are completely different. Okay. So within this same approach based on equivalent reconciliation, we may define also another equivalent notation that is based on a results that holds under some reasonable hypothesis from the biological point of view. For example, that the cost of losses is not negative, and this is absolutely reasonable from a biological point of view. And the idea is this, that two reconciliation are in fact the same if and only if they have the same set of host switches. And so on this base, we can do the following. So this is a host tree and a parasite tree, and this is a reconciliation, and this is the same host tree and same parasite tree, and this is another reconciliation. So we are saying that these two reconciliations are equivalent if for every parasite here that is not associated to a host switch event, for instance, this node and this node, they are all the same on the two reconciliation. And in fact, you can see they are mapped on the same nodes. On the contrary, for every host switch, that is every dotted line, let me call the starting node of the host switch can move on freely somehow on the path between the node, the host node where its father is mapped, and the host node where its children is mapped. And in order to highlight this freedom, we will call sliding path this path. And so you can see, since we are mapping this node here, and in another reconciliation, we map it here, then we can consider these two reconciliation as equivalent. Now, I would like to highlight that the partition of reconciliation induced by this equivalence relation is finer than the partition induced by the event vector, because, of course, two reconciliations that are equivalent with respect to this equivalence concept will have the same even vector, but what happens is that this equivalence distinguishes to these two reconciliation, and this is in agreement with the fact that the even vector was not able to distinguish different reconciliation, while this equivalence can. Now, also this approach, this has a problem, and the problem is that in order to extract a representative reconciliation for every class, we need to enumerate all the optimal solution, recognize which ones are equivalent, and then pick one. Now, of course, this can be found, and it works very well when the number of reconciliation is even quite large, but not too much. But it is impossible for very, very large data sets, like, for instance, this Wolbachia, that is an example of huge data sets in which the number of reconciliation is 10 to the 42, where we are not able, of course, to enumerate all of them in order to recognize just one for every set. And so the question is whether it's possible to enumerate directly without passing through the total enumeration. We want to enumerate directly one representative for every equivalent class. Now, this has been done recently, but not for this equivalence that is biologically meaningful, but for three rather artificial notions of equivalence. Anyway, it is an important step towards the solution of this huge problem. And so as open problem, I want to propose this one. So try to explore the connection between the equivalence that I proposed now, and that is in the previous paper, and determine whether it is possible to exploit the polynomial delay algorithm that are exploited in the last paper without passing through the enumeration of all the reconciliation. And another problem, of course, could be the one of defining other biologically meaningful notion of equivalence for which such polynomial delay enumeration algorithm exists. This is a really interesting open problem. Okay, fine. Now I would like to go to the third problem. So once that one enumerates all the optimal reconciliation and chooses which one to show to biologists, now it is necessary to provide a nice visualization of them. And so here I would like to show you some proposal again in the literature. So in this case, the input of the problems is not only the two trees HP and Phi, but also directly the reconciliation. What we want to do is to draw the tree H, the tree P inside somehow or connected to H, so that the reconciliation is shown in a nice and clear way. Now, in the literature, there are essentially three main strategies. The first one is this one. We to represent, it consists in representing the trees one close to the other one. Okay. The second one consists in drawing the host tree as a pipe-shaped tree and the parasite inside it, as I show in the previous drawings. And the third approach is to assume that host trees are not completely certain, and so just to draw a shadowed shape and then to put inside the parasite tree. These are the three approaches. Just to give you a very, very quick example of what happened in the literature, I want to show you, just show drawings. So this is an example of a tool that exists in the literature that follows the first approach. And I just want to highlight here that you see, here the things are not very clear. No, this is a problem. And this, so in the first approach, the drawing were rectilinear, or in this case, it's orthogonal, but anyway, the approach is very similar. And also here you see everything is cluttered. It is not exactly clear at the first look where things go. This is a very nice example of the second approach. One of the problems of this approach can be seen in this node. I hope you can see the pointer of my mouse. So you see in this node, everything is very close together, so you cannot see very well what happens. And this is another approach that is more or less in the middle between second and third strategy, because the host tree is defined, but not too much. But this is one of the first tools that visualize reconciliation. And this is the last example I wanted to show you that is completely in the third approach. But also here you see there are some problems. Everything is again cluttered and all together. So which is another possible approach that I would like to propose, is to draw the parasite tree as an orthogonal downward drawing. And this means that, of course, the parasite edges never go up in the drawing. They have to go to the bottom. And the host tree is drawn according to the space filling paradigm. Now, InfoVis people would call this an I-cycle drawing. And but the difference with the structure is that we force the leaves to touch the bottom size of the bounding box in order to represent that is the current time. Of course, these two drawings must be presented together, and this is the reconciliation. Now you can see that the representation is not ambiguous anymore, since every parasite is drawn inside its corresponding host, is not cluttered at all. And why this? Because you see, we can grow the height of the host nodes in order to contain all their parasites. So things are very nice. And moreover, we may also draw the hosts in a slightly slanted way in order to suggest whether a node is either a left or a right child of its father. And so with this approach, things are very clear because, for instance, you see, whenever you notice that there is an edge traversing a host node, so a rectangle, then you will have the intuition that that is a loss. Instead, you can understand that there is a duplication because, as in this case, for instance, because you will notice that both the children of that nodes will go towards the same branch of the subtree. So in this case, you see both of them goes towards the right one because they traverse this yellow right child. And of course, host switches are visible because they are dotted lines, and anyway, you can see them. Okay. Moreover, in this way, we can solve a lot of problems. For instance, look at this. Here in this case, you have that it is not very clear how things go, which is the children going to the left and which one go to the right. While if you draw with our settings, everything is very intuitive at the first look. And this is the important thing. Moreover, this approach is also able to keep mental map. What does it mean? In these tools is also possible to visualize not only one reconciliation, but many together, corresponding to the same pair of trees. Well, for instance, this tool, Coffee Trees, that works quite well, has the problem that it's not a problem from one side, but I mean, so they try to minimize the number of crossings. But this means that even changing very slightly the reconciliation, maybe the drawing of the host changes completely. And so the mental map of the reader is totally lost. While what we do is also to check whether is it possible to minimize the number of crossings, but we consider all the reconciliation as a whole and try to find the drawing of the host that is able to globally minimize the total number of crossings over all reconciliation. And this implies that probably on a single reconciliation, we have some crossing more, but the drawing of the host remains exactly the same for all the drawings. And so the reader can immediately understand whether two reconciliations are similar or not. And this is another example in which you see, this is what I showed you before. Here, there are many nodes cluttered inside a very small portion of the plane, while in this case, you have everything very clear because we can lengthen the height of this rectangle and proceed in such a way that everything is correctly fit inside. Okay. Now, in order to increase the readability of the drawing, we study the number of crossings, as I told you before, and realize a very nice property of this reconciliation. And that is that the number of crossing does not depend on the input reconciliation, but on the instance itself. Indeed, if we consider the so-called tanglegram, that is this object composed by the host tree, that is the above one, the parasite tree, that is the bottom one, and the leaf mapping function, that is somehow this bipartite graph in the middle. Well, we prove that if all this object, so all this object is planar, so can be drawn without any crossing, if and only if every reconciliation on this instance can be drawn without crossings. So this is a very nice property because we will know that if we have a planar instance, then all the its reconciliation will be drawn without crossings. If, on the contrary, the instance is not planar, then it turns out to be MP hard to understand how many crossings it needs to be drawn. Okay, which are the open problems on this in this case? Essentially, it would be interesting to have information on this drawing. In particular, there are some papers in which it is highlighted the fact that it's important to decorate the data set with some additional information, for instance, some geographical information. So we thought that a possibility is to put in correspondence geographical information with colors, for instance, and then what about proposing a drawing that try to put together the nodes with the same or similar colors, just to show to biologists that all those animals live together. So it would be a very interesting approach. But unfortunately, the drawing becomes a mess, of course, very, very easily, because in this way, a huge number of crossings is introduced. So everything is open, and it's it's ready, I mean, to think new approaches and new things. Okay, now I don't know whether I have time or not. How much time I have, Saidur?
Okay, you can talk, say, more 5 minutes. 5 minutes.
5 minutes. Okay, so I will be very, very fast in this last part, and then I will conclude. So a very last problem that has something to do with reconciliation, although in a different way, is this one, the problem of routing and unrooting tree. So here we are in the context of gene species instead of parasite host. First of all, why this different? Because as you can imagine, when we have to reconstruct a phylogenetic tree starting from animals, let's fix the idea on animals, but of course you can use whatever you like, that live now, so you have to go back in the time. But you have the help of fossils and things like this, so you can order somehow the ancients going from the current time and back into the time. When we use instead the context of genes and species, what we have is that the gene tree is not so sure for what concerns the times, no? Because we have that there are some transformations of genes from a species to another one, but who can say which gene come before than another one? Moreover, often the transformation involving genes are usually bidirectional. So you can do, no, if for instance, if you switch a pair of things inside the genes, of course, you can do in both directions. So it is difficult to root this gene tree. And so while the species trees are rooted because of the help of fossils and things like this, unfortunately, gene trees are difficult to root. So which is the idea that is present in the literature? Try to exploit reconciliation in order to transform an unrooted gene tree into a rooted one. And why we can do this? Because while between a parasite and a host, we are not sure that they co-evolved. On the contrary, for what concerns species and genes, well, we are sure they co-evolved, no? Because to a modification of the gene necessarily correspond a modification of the species and vice versa. So we can reconciliate these two trees and try to understand which is the root. So now the approach, the naive approach that is used in the literature is the following. So take an unrooted tree. For every edge of this tree, you can put a dummy root inside, root the tree with respect to this root, and try to reconcile this tree on the species tree. Of course, you will get a cost for this reconciliation, and you can annotate on the edge corresponding to where you put the root. Now, what we have to do is that look for the edge with the minimum value, and that edge will be hopefully the edge where it is better to put the root. The time cost, of course, is in general quadratic, no? Because you have to perform a kind of search for every edge. But what is nice is that if we exclude the possibility of having switches, host switches that in this case are called gene transfer, then it is possible also to handle these things in linear time, so very efficiently. But the problem of this approach is that often it happens that there can be many ages with optimal cost. So it is not clear which one we have to choose in order to root the tree. Now, it has been proposed some years ago, a very elegant and nice concept, the one of the so-called plateau, that is the subforest of the gene tree induced by the ages having the minimum cost. And so these guys proved that if we do not allow the host switches, so the transfer, then here we have a picture, then this plateau is connected. So it means that the minimum is all together. And this is very interesting because we do not know exactly where to position the root, but we have an intuition because it will be anyway in a place inside a connected zone. It's something, okay? But unfortunately, it has been proved that if we introduce again the host switches, so the transfer, then the plateau is no longer connected. So what we did in 1 minute, we tried to study the transition from the model without switches to the model with switches. And just in order to highlight this transition, we introduce the case in which gene transfer can happen, but they can be only very short. So they can happen only between siblings. And in this case, we prove that there are infinite instances for which the plateau is not connected, and its component can be also arbitrary far. Of course, these instances are artificial, but it's just to show that they can exist. But on the other side, we proved also that there exists still a linear time algorithm that is able to produce all these labels and so to choose the minimum ones. And so proving that somehow this transition from the model without transfer to the model with transfer is not sudden, but there are some things that moves slowly. So the main open problems in this context is that is the following. So what if we allow gene transfer to be longer? Are we able to keep this linear time algorithm, or at a certain point we will go to quadratic anymore? Okay, so with this, oops, I have concluded. I just want to thank all my co-authors that are depicted here in this slide. And of course, I would like to thank all of you for your attention. Okay. Are there any questions?
Thank you, Tj Ana, for your wonderful talk. Actually, I am very much impressed that how you relate the evolved phenomena of host and parasites to the modern graph drawing problems, and that is, you relate the Darwin age with the current graph drawing age. So I'm very much impressed to hear your talk. I hope audience has may have some questions. I invite some questions from the audience. Please, if you have some questions, please raise your hand, or you can ask directly. You can raise your hand, or you can even ask directly your question to Tj Ana. I think, yeah, Beppe has some questions.
Hi,
Yeah.
Beppe.
Yes, hello, Tj Ana. It's nice to see you, and
Hi.
thank you for the very nice talk. I was wondering, you know, in the representation where you combine these rectangular representations of trees and the straight line or orthogonal representation of trees, I have the feeling that the rectangular representation is constructed starting from a one-page book embedding. That's my feeling by looking at the figures. And so the question is whether you thought about other possible representations, rectangular representation of trees. You know, all these tree map representations that are quite popular. I wonder if you consider those or not, and if not, why?
No, we were looking for a representation that were able to solve the problems of the other tools somehow. So this iCycle drawing came to our minds, and we concentrate on that one. But yes, it's a good idea to think to other kinds of representation. The idea was to exploit two different criteria for the two trees. So we like this iCycle for the host and orthogonal drawing from the other one. But of course, we can think to the idea of using other approaches for the two trees and see what happens. Okay.
Okay, I just asked a question that you showed that you showed some methods of reducing that is size of cardinality of constellation trees. You introduced some equivalence classes. That is, yeah. And in equivalence classes, you are classifying, that is, you are putting as a class of graphs in the same class. And will not it restrict its application to the real biological problems?
I'm not sure I understood it, because I can hear you not very well, but can you repeat? So you
Okay.
mean whether what you put together in the same class? No?
Yes, you are considering a say, similar classes of trees in the same class, an equivalent class, and then treating and then considering that is finding the optimal reconciliation, I think. And,
yeah, the idea is that.
But my question is, will not it restrict its applications in real biological problems?
Yes, this is the idea. I mean, since there are too many reconciliations, what you want to do is to reduce the number. But of course, you don't want to pick them at random, but you would like to select with the biological meaning. So the idea is, how can I select just one from a bunch without and avoiding the possibility of throwing out something that instead is important from a biological point of view, no? So I have to put together something that is biologically similar. Otherwise, biologists will lose some information.
Okay, yes. Okay. Thank you. I think there is more question. Tj Ana, do you want to ask a question?
Yes, I have one question. So when you are showing the tree reconciliations in your presentation, I noticed that there are some examples where you have the height of the host tree to be longer than the height of the parasite tree because you are skipping some of the intermediate nodes. So I'm wondering, is there any cost associated with skipping intermediate nodes when you are doing the tree reconciliation?
So in fact, those were just examples because in practice, parasite trees are wider because usually bacteria and things like this evolve much quicker than big animals. But anyway, so there is a concept, a time concept going up, but unfortunately, one of the problems of this reconciliation is that times are absolutely uncertain. And this is the reason why we need all this stuff, because if we had information about time, there is also a wide literature in this context. I mean, if there is a special way, for instance, using fossils, so that you can exactly put a date on a node, then things become much easier. But this is a very rare event, unfortunately, no? So you have to guess somehow. This is the problem. And so you have no knowledge about how far you have to go from one node to the other one.
And another question, as far as I know, phylogenetic trees are weighted trees, right? You have age weights based on the distance between, connected, like parent species and children species. Now, when you assign costs to the mutations, like host transfers and other mutations, how do you assign the cost to that reconciliation? Is that related to the weight of the tree, or is it some independent measure?
No, so what you are saying is that is the example I told you before. I mean, the dated tree. So if I know the dates, then I can decorate the tree with these labels. And this is very easy. But usually they are not labeled. But anyway, in both cases, the cost is based on the number of events. So how many co-speciation, how many duplication, and so on. You assign a cost to every one of these 4 events. And once you determine the reconciliation, you simply look which is the cost of this reconciliation with respect to the events, not to the weight of the tree.
Okay. Is there any other question from the audience? No. Then thank you, Tj Ana, for your nice talk. And please let us give a big hand to you.
Thank you.
So our
okay, Mr. Sayyidul Rahman.
Yeah.
Okay. Thanks to Mrs. Tj Ana Kalamundi and Mr. Sayyidul Rahman as a chair and the invited speaker in this agenda. Now we are going to the next session. Is contributor talk 3. and the topic is computational geometry. As a chair is Mrs. Minatide.
Actually, I think that there is a tea break now.
Oh yeah, tea break.
Yes. So
I'm sorry.
Tea break until say 3:15, 3 o'clock, and then next session will start. Okay.
Okay, thank you, Mr. Sayyid Rahman. We are going to the break now. Yeah.
Thank you, Tj Ana and Betsy. You have joined. I think it is very early in the morning in your time.
It was just 7:30. What about Beppe? He was here from before, I guess, no?
Yeah.
Beppe Liotta, I mean, is in Italy also. Probably he had to wake up much earlier, no?
No, actually, our time now, we that is just difference of with Indonesian time is only 1 hour in Bangladesh.
You, yes. No, I was speaking about Beppe Liotta, that was the chair of the previous session, no? Yeah. I saw him, but it should be in Italy also. Or maybe not, I don't know. Okay, so things are going well. Anyway, I'm
yes.
happy about it. Yeah. Okay. So I will stay with you for a while, and then I have to go to my class, but I hope to connect later and tomorrow for other talks.
Yes, and also invite you to join in the business meeting.
Okay.
In the afternoon, tomorrow.
Okay, so.
Tj Ana, thank you for the very nice talk. I'm also in Europe, and therefore I'm very tired still. So I went up tonight at 3 o'clock because for the opening, I wanted to be there for the opening. And but then I was just too tired and made a short break. But now I'm online again. But still, it's hard to, to stay awake all the time.
Actually, in Germany, it was in the midnight, so I did
3
not
o'clock.
ask Professor Peter Mutzel to join the inaugural session. But yeah, she is very kind that she joined the inaugural session.
But yeah, during your talk now, I wondered if there is a connection to the graph edit distance. It is some form of the graph edit distance. So you have two trees, and you are interested in the sequence of operations to bring one tree to the other. But it's not the same because you have some restrictions, and one of your trees is much smaller than the others. Yeah, maybe it's too far away, I guess.
No, there is some connection. Yeah, what I show you about the distance, yes, has much to do with the distance between trees.
Yeah.
There are some, yes, there are some ideas that are in common. The problem is just that we have always this biology, so we should keep into account that the things we do have a meaning for biologists, otherwise they do not care, of course. But yes, there is a tight connection. Yes, there are some papers comparing these distances between trees and try to understand which is better able to convey the biological information.
Because I learned that biologists very often use this because it's so flexible. You can just assign any cost to any operation. But of course, here you need really to buy subtrees, and maybe then it's much more difficult. Yeah. But thank you. That's very
I
interesting.
have not studied this part in detail, so I cannot. I don't know. I remember there is this distance that is called Robinson Fultz. I don't know if you refer to something like this. No.
This I have not heard, but I'm also not into biology so much. So I just studied these graphs. So I work a lot on graph similarity, and at some point I looked at the graph edit distance, because I very often in biological papers I read that this distance has the advantage that it's so flexible with the costs. But of course, it's very hard to come up with solutions. It's very hard. And so very tidy instances can be solved exactly. And then at the end, they use some heuristics. Yeah.
Ah, okay. How is it called, this distance?
I wrote it in the chat.
Graph edit distance. Ah, yes. Graph edit. Yes, it's something similar to what I show you, but yes, the problem is that it is MP hard to understand, no? If I will remember. The problem that we have is that the distances that are easy to compute are full somehow, while the distance that are really meaningful, and this is one of them, yes, are unfortunately MP hard to compute. And so you cannot exploit. So yeah, this is a drawback that is not easy to solve.
Yeah,
yes.
That's true.
But this is a very interesting topic. Yes, there are a lot of new things that you can apply and invent in order to let things work.
Yeah. Okay. Then thank you. So I will.
Thank you to you.
Thank you very much.
Wait. We'll start actually at 1:30. Come to the last session of today's WALCOM. So this is the session dedicated to computational geometry, and we'll have 3 contributed talk in this session. I am very glad to chair the session, and I would like to thank Professor Shoidur Rahman for inviting me to chair the session. Okay, I would like to invite Professor Shujo Yamamoto to present the first paper of this session. The title of the presentation is Vertex to Point Conflict-Free Chromatic Guarding is NP-hard. So Professor Shujo, please.
Okay, thank you very much. Can you hear me? Okay. The title is Vertex to Point Conflict-Free Chromatic Guarding is NP-hard. My name is Chuzo Iwamoto. Okay. The artery problem is to find a set of guards who can observe the interior of the polygon. Suppose that a guard is placed on that position, then the red area is observed. And if we add 4 more guards, then every point in the polygon can be observed by at least one guard. In this talk, I study chromatic art gallery problem. Suppose that a polygon is given, and I want to use a codeless form system on this floor. Suppose that a form base is placed at that position, then in the red area, we can use a handset. However, there is a white space, so we need another form base to cover the remaining area. However, if we add another form base, then radio wave interference occurs. So which base should the handset be connected to? In order to avoid such a situation, we use a codeless phone system of different company. Okay, then each handset can communicate with its own phone base. There is no interference. Okay. Chromatic art gallery problem is to find a colored guard set such that no interference occurs. Okay. In this talk, we study conflict-free chromatic art gallery problem. Suppose that a polygon is given, and if you place a guard, then the red area is observed, and we need 2 more guards to observe every point in the polygon. Okay. Okay. Consider a point. Okay. This point is seen by 1 red guard and 2 blue guards. Okay. The guard set is said to be conflict-free if any point can see a guard of a unique color among all the visible guards. Okay. I explain the definition by using figure. Among all the visible guards, there are 3 guards. Okay. Any point can see a guard of a unique color. Okay. This is a conflict-free condition. Okay. Conflict-free is stated another way. Okay. Each point is seen by a guard whose color appears exactly once among the visible guards. Okay. So at least one of the colors seen by every point is unique. Okay. This is a conflict-free condition. Okay. The definition of conflict-free chromatic art gallery problem is as follows. The instance is polygon P with holes. And the question is to decide whether there exists a conflict-free chromatic guard set for polygon P with holes when the number of colors is 2. Okay. There are 3 variants of art gallery problem: point-to-point guarding problem, vertex-to-point guarding problem, and vertex-vertex guarding problem. Point-to-point case is the most standard one. Guards are placed on any point inside the polygon, and guards observe all points inside the polygon. This is point-to-point guarding problem. On the other hand, vertex point case, guards are placed on vertices. Suppose that a guard is placed on a vertex, then the red area is observed. And guards observe all points inside the polygon. In the figure, there are 2 areas which have not yet been covered. So we need 2 more guards on 2 vertices. This is vertex-to-point case. And vertex-to-vertex case, guards are placed on vertices. And guards observe all vertices of the polygon. Okay. This guard observes 8 vertices. So there are three vertices which have not yet been observed. So we have to add 2 more guards on vertices. This is vertex-to-vertex case. Okay, this is the result. In the vertex-to-vertex case, it was known that conflict-free chromatic art gallery problem is not to be NP-hard. This was proved by Kagirichi, 2019. In the same paper, vertex-to-point case, conflict-free chromatic art gallery problem is an open problem. In this talk, I solve this open problem. It is shown that vertex point conflict-free chromatic art gallery problem is NP hard. The point-to-point case is still an open problem. Okay, I consider vertex point case in this talk. Okay, main result: vertex point conflict-free chromatic art gallery problem for polygons with holes is NP hard when the number of colors is 2. Okay, I'll give the proof. We construct a polynomial time transformation from an instance of 3SAT to polygon P such that 3SAT is satisfiable if and only if polygon has 2 colored guard set. Okay, I start with explaining 3SAT. Okay, 3 satisfiability problem, 3SAT. The instance is a set of variables and a set of clauses where each clause is a disjunction of 3 literals. The question is to decide whether there is a satisfying true assignment for all clauses. For this instance, the answer is yes, because 1101 satisfies all the clauses. 1101 satisfies all the clauses. In this talk, we use clause-linked planar 3SAT, which is defined as follows. Clauses are connected by a planar chain, and variables are embedded on the plane so that relations between clauses and variables are represented by a planar graph. It is known that clause-linked planar 3SAT is NP complete. Okay, now I'll give a transformation from 3SAT to a polygon P. Okay. Okay, this polygon is the top level description of the polygon. Okay, X1, X2, X3, X4, and C1, C2, C3. Okay. C1, C2, and C3. Okay. Okay, I'll explain the details of the variable gadget xi. Okay. This is variable gadget x for xi when the value is 1, when the value is 0. Okay. And this is a variable gadget. Variable gadget contains ball-shaped gadget. Okay. Ball-shaped gadget. Okay. Ball-shaped gadget. Okay. This is simplified illustration of the ball-shaped gadget, and this is the detailed illustration of the ball-shaped gadget. Okay. In this talk, okay, only the ball-shaped gadget is not my original, invented by Kagirichi 2019. Ball-shaped gadget has the following property. Okay, consider figure B. Okay. Consider vertex P1 or P2. Okay. A guard on P1 can see all points in the gadget. P1 can see all points in the gadget. However, if no guard is placed on P1 or P2, if no guard is placed on P1 or P2, then we must place 2 pairs of red and blue guards. 1 pair, 2 pair. Okay, because of the following reason. Okay, this part is convex, and this part is also convex. Therefore, if we place a guard, then there are 2 vertices which have not yet been covered. In order to observe these vertices, we need another guard, blue guard. Similarly, if we place a guard, then there are 2 vertices which have not yet been covered. So in order to cover these 2 vertices, we need another guard of color blue. However, this guard set is not conflict-free. We consider this area. Okay, this area is seen by 2 red guards and 2 blue guards. No unique color. Therefore, this guard set is not conflict-free. Therefore, under the conflict-free condition, figure C is invalid placement of guards. Okay, B is valid. Okay. A guard must be placed on P1 or P2, under the conflict-free condition. Okay, now go back to variable gadget. And this is pocket gadget. Okay, pocket gadget. This is pocket gadget, and this is simplified illustration, and this is detailed illustration. Okay, red and blue guards can see all points inside the pocket in the conflict-free condition. Okay. So if we place red and blue guards, then this is a visibility line from red, and this is a visibility line from blue. Okay. Blue enters deeper than red. Okay. Blue enters deeper than red. Therefore, on B1, we must place red guard. Okay. So B1 emits a red beam upward. This is the assignment xi equals 0. And this is assignment xi equals 1. Okay. By switching red and blue, we obtain 1, 0, 1, 0, 1. Okay. By switching red and blue, we obtain 1, 0. This is left turn gadget. Suppose that red, blue guards are placed, then this area is seen by 2 red and 1 blue guards. And blue is unique color. Consider base gadget B4. On B4, we must place red guard. 2 red is replaced with 3, and blue is still a unique color. Now consider this area. This area is now seen by 1 red guard. So we must place red, blue guards. Okay. Then that area is seen by 3 red and 1 blue guard, and blue is still unique color. Okay. This is left turn gadget. Okay. If B1 emits a red beam upwards, then B5 emits red beam leftward. Okay. Left turn gadget is simply illustrated by this figure. This is branching gadget. If B1 emits a red beam, then B11 and 12 emit red beam to the left. This is the simplified illustration. NOA gadget. Suppose that xi1 is 0 and xi2 is 0. Okay. Then we must place red and red guards, and we must place blue guard. Then we must place blue, red guards. Okay. Therefore, if xi1 and xi2 are 0, then the gadget outputs 1. By switching red and blue, we obtain this figure. Okay. Okay. We obtain 2 figures. Okay. These figures are when xi1 and xi2 are the same. The case where xi1 and xi2 are different is explained later. Not gadget. Not gadget is composed of branching gadget followed by NOA gadget. And OR gadget is composed of NOA gadget followed by NOT gadget. Suppose that xi is 1, then NOA gadget outputs xi bar equals 0. Therefore, if xi is 1, then NOT gadget output xi bar equals 0. If 1 and 1 are given to NOA gadget, then it outputs 0 and NOT outputs 1. Okay, this is OR gadget. Okay, by switching red and blue, we obtain this figure. Okay, we obtain 2 figures. The case where xi and xi2 are different is explained later. Okay, this is closed gadget. If 3 inputs are 0, then closed gadget output 0. Okay. Now go back to NOA gadget when xi1 and xi2 are different. Suppose that xi1 is 0 and xi2 is 1. Then red and blue guard must be placed, and we can place red guard at that position. Then we place red, blue guards. Okay. Therefore, if xi and xi2 are different, then the gadget can output 0. Okay. There is such a conflict-free gadget which outputs 0. or gadget, if xi and xi2 are different, then no gadget can output 0 and not gadget output 1. Therefore, gadget can output 1. Okay. There exists such a conflict-free gadget. Therefore, this is closed gadget. At least one, suppose that at least one of the three inputs is 1, then the gadget, suppose that 1, 0, 0 is given, then the gadget can output value 1, up and down out. Okay, this is a transformation, x1, x2, x3, x4, c1, c2, c3, x1, x2, x3, x4. Please recall that 1, 1, 0, 1 satisfies all the clauses. 1, 1, 0, 1. Okay. C1 is satisfied, C2 is satisfied, C3 is satisfied. Okay, C1 receives red, blue beams. Therefore, C1 emits blue beam up and downward. Okay, C2 and C3. Okay, there are X NOR gadget. Okay, X NOR gadget. If X NOR gadget receives two beams of the same color, then red, blue, and red, blue guards are placed, and on B13, we can place a blue guard. However, if X NOR gadget receives two different colors, then blue, red guards are placed, this part is blue, red, blue guards are placed, this part is red. Therefore, on B13, neither blue guard nor red guard can be placed on B13. There is no answer. Okay. So in this case, there are answers. Finally, okay, our 3SAT contains dummy clause, which composed of dummy variables, and dummy variables must be 1. Okay. Dummy clause and dummy variables are used so that we want to fix the relation between color blue and value 1, and color red is value 0. By this construction, 3SAT is satisfiable if and only if polygon has other two color guard set. Okay, this is my presentation. I prove that vertex point conflict-free chromatic algebraic problem is NP hard when the number of colors is 2. Okay, thank you very much for your attention.
Thank you. So do anyone of you have some questions? Please feel free to ask questions. Otherwise, I also have some question. So, so here you consider the problem for polygons with holes. So how about with, I mean, for simple polygon, is it some algorithm is known, or maybe the problem will be again NP hard? What is your feeling about that?
Sorry, I can't hear you.
Okay, I see. So my question was something like this. So you have studied this for polygon with holes, right? So how about for simple polygons that doesn't have any hole? For that, the problem is it a polynomial, or the complexity will be still NP hard? What is your feeling?
For me, sorry, I have no idea. Sorry.
Okay. Okay, I think
actually, is there any result on polygon without holes for this problem?
In my presentation, in my proof, hole is essential. If no hole, then theorem doesn't hold. Removing holes is interesting open problem. Thank you very much.
Okay.
Okay, let us thank the speaker. And yeah, so we are moving to the next talk. The title of the talk is The Polygon Bonding Problem, and it will be presented by Evans. So let us invite.
Okay, I'll start sharing my screen.
Rebecca will be presenting. Okay.
Hi. Okay, so hopefully that works.
Yes, please. Go ahead.
Okay. Hello everyone, I'm Rebecca, and today I'll be talking about the polygon burning problem, and this is joint work with Will Evans. So this problem is very much related to the metric K-center problem, which is quite a fundamental problem in theoretical computer science as well as operations research. So given a set of endpoints representing client or demand locations, the K-center problem asks to find a set of K points for placing facilities such that the maximum distance from any demand to its nearest facility is minimized. So if we look at it geometrically, the goal is to find the centers of K equal radius balls whose union covers demand points and whose common radius is as small as possible. So it is well known that the K-center problem is NP hard, and in fact, it's NP hard to approximate within a factor of less than 2. However, two approximation algorithms exist. So in many real-world applications, demands may be distributed throughout an area rather than restricted to a discrete set. So for example, if we consider the problem of placing post offices in a district, such that the worst case travel time of any individual to their nearest post office is minimized, we have a continuous set of demand, essentially. So often, regions of demand can be modeled using polygonal domains, and these domains may or may not contain holes. And on these domains, we usually consider the geodesic metric or the shortest path metric. So here the dashed lines indicate the shortest path connecting S and T. And this path is contained entirely inside the polygon. And the geodesic distance between these 2 points would be the Euclidean length of this path. So naturally, the geodesic K-center problem on a polygonal domain has received considerable attention. It asks to find K-center points inside the polygon, such that the maximum distance from any point in the polygon to its closest center is minimized. It might be surprising that there's no results for arbitrary K. In fact, for simple polygons, only the case where K equals 1 and 2 have been considered. And for general polygonal domains, only the case where K equals 1 has been considered. So in practice, facilities are often restricted to feasible locations, and hence there has been some interest in constrained versions of the geodesic K-center problem. So for example, Du and Xu, they looked at constraining centers to the boundary of a convex polygon, and they provided an approximation algorithm for this problem. And for O et al., they looked at computing the one center of a simple polygon constrained to a set of line segments or simple polygonal regions inside the polygon. So for us, we're looking at a new variant of the geodesic K-center problem. And here we're restricting facilities to the vertices of the polygonal domain. So if we view each vertex as a site to start a fire, the goal essentially is to select K sites such that the fires burning simultaneously and uniformly from these sites consume the polygon entirely as quickly as possible. So our first step would be to prove that this problem is NP hard. So recall that the vertex cover of a graph is a set of vertices that includes at least one endpoint of every edge of the graph. And here we're looking at the 4-planar vertex cover problem. So given a planar graph G with max degree 4 and an integer kappa, does G contain a vertex cover of size at most K? And we'll be reducing this problem to our polygon burning problem. So the first step we take is we compute an orthogonal drawing of the graph G. And here we'll have ON bends, and this drawing will be on an integer grid of ON squared area. And next we'll position vertices, we'll add vertices to the bends of this drawing. And then we'll further divide the drawing by adding vertices along its straight line segments. And here we're like a little bit careful. We require each divvied up segment to be between 1/3 and 1/4 in length. And in addition, we want the total number of line segments replacing this original edge in the orthogonal drawing to be, so we want the total number of line segments replacing this original edge to be odd. And this essentially lets us have a known vertex cover size for this new graph G prime corresponding to this drawing. So next step is to convert this drawing G prime to a polygonal domain. And what we do essentially is to fatten each edge by 2 epsilon as shown here. And in the paper, we proved the following lemma. So G has a vertex cover of size at most kappa if and only if the polygon constructed from this modified graph G prime can be burned in time 1/3 plus 3 epsilon using f of kappa sites. And f of kappa would be polynomial in N. And as a result of this lemma, we basically show like the polygon burning problem is NP hard in general for polygonal domains. And in the paper, we provide a 3 approximation algorithm for polygon burning by relating the problem to the classical K-center problem we described at the beginning of the presentation. So having established hardness, we'll shift our attention to a special case, a special family of polygons on which we can solve the polygon burning problem in polynomial time using dynamic programming. And we'll call these polygons sliceable. So a sliceable polygon is convex and it contains no Werner vertex from the Werner diagram of its vertices. So a Werner diagram consists of Werner regions. And so we see the dashed lines here. A Werner region is a set of points that share the same closest vertex of P. And when 2 adjacent Werner regions meet, they form an edge. So these dashed lines actually indicate the edges. And Werner vertices, highlighted in yellow, is where more than 3 regions share a point. So here the polygon doesn't contain any Werner vertices, and hence it is sliceable by our definition. And the key idea is that sliceable polygons emit a natural ordering of separable subproblems. And so first we'll explore and exploit this property by considering a degenerate type of polygon, polygons in 1 dimension. So these polygons are sliceable just because their Werner diagram has no Werner vertices. So of course they themselves cannot contain any Werner vertices. So we'll define linear IK to be the minimum time to burn the polygon between VI and VN using K sites in addition to burn site VI. So using that, we can then express the time to burn the entire polygon optimally using this expression. So for each choice of first burn site, VI, we essentially need to consider the time required to burn from VI back to V1. And we also have to consider the time to burn the remainder of the polygon, so here in blue, given that VI is the first site selected as a burn site. And essentially the minimum here is allowing us to choose the best VI to do the job. So the recurrence linear IK can be defined similarly by choosing the next burn site following VI, so next burn site VJ, where we're minimizing the larger of 2 values. And the first value is really like the time to burn the polygon between VI and VJ, and that is really the distance, 1/2 of the distance between them. And then we're also looking at the time to burn the remainder of the polygon, which is in blue here. So summarizing that, we get our recurrence relations. And from these recurrences, we can develop a dynamic programming algorithm, and we could essentially solve polygon burning in kn² time on 1D polygons. So we see that for 1D polygons, there's a natural ordering of subproblems, and we show that this property persists in like a more general case of sliceable polygons. And this property is captured in this lemma shown here. So the vertices of a sliceable polygon can be ordered such that any burn site burn sites U, V, W, the region of for any burn sites U, V, and W. The region of P burned from U, so here in orange, does not share a boundary with the region of P burned from site W. So in order to prove this lemma, we'll consider two parts. So for part one, for sliceable P, each region in the Warner diagram of P shares a boundary with at most two other Warner regions. So we could prove this by contradiction. So we could suppose that a vertex of P shares Warner edges crossing P with 3 or more vertices. And in the paper, we showed that this implies the existence of a sliceable quadrilateral that has the same property. However, we'll show that no such quadrilateral can actually exist. So for quadrilateral URST to be sliceable, its Warner vertices here in yellow must lie outside of it. So looking at that, we notice that our angle RUS has to be obtuse in order for this circumcenter, or the Warner vertex, to be outside the polygon. And similarly, we need TUS to be also obtuse. However, this implies that RUT would be reflex, and hence the quadrilateral won't be convex and not sliceable. So this contradiction establishes the above conclusion. So for part two, we're proving that the graph joining two vertices, if they share a boundary, Warner boundary, is connected and thus forms a path. And this path defines the ordering of vertices. So we can assume for contradiction that the graph has more than one connected component. And that this essentially means that there's no intercomponent vertices forming Warner boundaries with each other in the Warner diagram of P. So it follows that the fires burning from separate connected components can never meet, and hence the polygon can't actually be burned entirely. And so that's a contradiction, and that essentially establishes P2. So we can adapt the recurrence relations from the 1D case quite easily to fit with the sliceable polygon, the general case. Here we note that Pij and Qij denote the intersections of the bisector of Vi and Vj with the polygon's boundaries. So the only thing we really tweak is this highlighted component. So that's the only thing we tweak from converting the 1D case to the sliceable polygon case. And we utilize more properties of sliceable polygons that we show in the paper. Okay. So this allows us to essentially solve polygon burning in OKn² time on sliceable polygons. So in conclusion, we have shown that polygon burning is NP hard on general polygonal domains, and the hardness remains open for simple and convex polygons. And then in the paper, we showed a polynomial time 3 approximation algorithm for the problem, and we do so, we essentially have the algorithm by considering the original k-center problem. And lastly, we showed that there exists OKn² algorithm for sliceable polygons, and it would be interesting to expand the class of polygons solvable using dynamic programming. Yeah, that is it.
Good. So thank you. So do any of you have some question? Please feel free to ask question to Rebecca directly, or maybe you can write also in the chat.
Hello.
Yes, Dibbayan is asking.
Yeah.
Please go ahead.
So, so does the hardness go through for orthogonal polygons as well?
So essentially for the hardness, we prove for general polygonal domain. So these are polygons that contain holes. So we have not shown hardness for simple and convex polygons, and that's an open question. Those are open questions.
Okay, so my other question is so what about terrains? Have you, what do you think about terrains? So for terrain polygons, so what do you think? the polygon burning is solvable in polynomial time for terrain polygons?
Sure. Wait, sorry, can you spell that out in the chat?
Okay, I will.
I think what you are asking about simple polygonal chain or something like that, Dibaya?
Yeah, the 1.5D terrains polygons. So it is common to consider problems in this particular class. Yeah.
So polygonal chain, let's say, if you are given. So I think that all the things are open.
Okay, so you're asking if we could like explore polygon burning on polygonal chains. Okay. Oh, yeah, that's a good question. I think that would very much be similar to just the K-center problem on graphs, or at least variations of the K-center problem on graphs, I think. But I'm not sure.
Okay, thank you.
I have one question. So you have this 3 approximation algorithm for polygons with holes for general polygons?
Yeah, yeah. Mm-hmm.
So for simple polygon, you have not studied, right? Without holes, whether one can have some algorithm which runs in polynomial time, or maybe the problem still is NP-hard in that.
Yeah.
Problem is very interesting. Yeah.
We don't know, yeah. I'm leaning towards that it might be NP-hard, but I'm not sure.
So do any of you have any more question? Please feel free to ask me because we have 2 minutes more time.
Yeah, so just one more question. So like this polygon burning is very close to this K-center problem. So what is the difference? Like, what is the main difference between these two problems?
Are you looking at the general K-center problem or the geodesic one on like polygon?
The geodesic.
Okay, I think the main difference is that for the geodesic problem, maybe I could, oops, okay. The geodesic K-center problem is actually, so the centers could be anywhere. And for ours, it could be on vertices. So our problem is actually a combinatorial optimization problem. So in the sense, like the flavor of it is a little bit different.
Okay, so it's like geodesic K-center, but you restrict the solution to be on the vertex.
Exactly. So the difference with that would be, so like we have a finite set of places that, where the sites could be, versus here like centers could be anywhere. So there's like an infinite possibilities.
Okay, thank you.
If no more question, let us thank the speaker. Okay, we can move to the next talk. So the next talk is, yes. I see. Yes, we can hear you. So next title of the talk is Reverse Shortest Path Problem in Weighted Unit Disk Graph, and it would be given by Yumin.
Yeah, thank you. Okay, okay, so let me share my screen. So, so because my time zone is in midnight hours, so please allow me to play the recorded video. Okay, so and I will ask your questions at the end. Okay. Hello everyone, my name is Yiming Zhao. Okay, can you hear the video?
Yes.
Okay, thank you. The paper I'm gonna present is reverse shortest path problem in weighted unit disk graphs. This is a joint work with my supervisor, Dr. Haitao Wang. Okay, let's start. Given a set P of n points and a parameter r which is larger than 0, a unit disk graph is an intersection graph of congruous disks centered at the points of P with a radius of r/2, which means an edge connects 2 points if the distance between these 2 points is at most r. we have two ways to assign weights to each edge. So in the unweighted case, each edge has a weight of 1. In the weighted case, the distance between these two endpoints is used as the weight of this edge. And the distance between 2 points is the length of a shortest path connecting these 2 points in the unit disk graph. And we can also define L1 unit disk graphs if the distance between 2 points is measured by the L1 metric. Next, we consider the reverse shortest path problem. We are given a parameter lambda, which is larger than 0 and 2 points S and T in P. And we need to compute the smallest parameter R, which is denoted as R star, such that the distance between S and T in unit disk graph with respect to parameter R star is at most lambda. Note that the distance between two fixed points S and T over the parameter R is monotonically decreasing. And there are some single source shortest path algorithms for unit disk graphs. For our two-weighted case, we have an algorithm which takes n log square n time. And for the unweighted unit disk graphs, we have n log n time algorithm for both L1 and L2 weighted case. If all the input points are pre-sorted by their x and y coordinates, then we can have a linear time algorithm. For the L1 weighted case, we have an algorithm of n log n time. And Cabello and Jesse have proved that the lower bound for the single source shortest path algorithm is n log n. And we also have some RSP algorithms for unit disk graphs. All of these algorithms based on an observation that R star must equal the distance of 2 points OP in all cases. Cabello and Jesse gave a straightforward solution which takes n to the 4 over 3 times log cubic n time in 2015 for L2 unweighted case. Wang and Zhao later gave two algorithms which take lambda times n log n time and another algorithm of n to the 5 over 4 times log to the 7 over 4 n time. The first one is good when lambda is small. Very recently, Kaz and Sharia gave a randomized algorithm whose expected running time is n to the 6 over 5 plus epsilon for both unweighted and weighted cases in L2 unit disk graphs. And in this paper, we give an L2 weighted algorithm which takes n to the 5 over 4 times log 5 over 2 n time. And we also solve the RSP problems in R1 unit disk graphs for both unweighted and weighted cases in n log cubic n time. And we also have a byproduct which is an L1 distance selection algorithm. This algorithm will report the case smallest L1 interpoint distance among n points. And the running time of this byproduct is n log cubic n time. Due to the time limit, I'll mainly focus on the L2 weighted algorithm. And our results have been presented in another workshop. We first give an overview of our algorithm. So the basic framework is to first define a decision problem, which is given a parameter R. We need to decide whether R is larger than or equal to R star. We have an observation that R is larger than or equal to R star if and only if the distance between S and T in unit disk graph with respect to parameter R is less than or equal to lambda. So we can use a single source shortest path algorithm as a decision algorithm. In this paper, we use the algorithm Wang and Xue, which is proposed in 2020. We refer to this algorithm as WX algorithm. The running time of WX algorithm is n log square n time. It's n log square n. The basic idea is to maintain an interval R1, R2. The left side is open and the right side is closed. And we ensure R star is in this interval. And we do a parametric search to shrink the interval. In this parametric search, we will parameterize the WX algorithm. So we first review the WX algorithm. In this algorithm, we will maintain an array called disk, which stores the candidate distance from S to each point. And the first step is to build a grid implicitly. And the side length of each cell is R over 2. we define a patch is a square area consisting of 5 times 5, which is 25 cells. And we define the cell of P is a cell that contains point P. And we define the patch of P is a patch whose central cell is cell of P, which is the big blue square in this example. And we define the unit disk of P is a unit disk centered at the point of P. And all neighboring points of P in the unit disk graph with respect to parameter R will lie in the gray region bounded by this big blue square in this figure. The basic idea is to pick a point Z with the minimum dist value in each iteration, and the dist values of points in the patch of Z will be updated. Before I enter the WX algorithm, let me introduce an important subroutine called update. So for two sets, U and V, the update subroutine will update the dist values for vertices in set V by using the dist values of vertices in set U. So in this example, for each red point V, we need to find the blue point QV from all these blue points lying in the unit disk centered at a point V, such that this formula, dist U plus the distance between U and V, is minimized. Okay, so and then the dist value of V will be updated to the minimum one of these two values, original one and the dist value of QV plus the distance between QV and V. And this is a framework of the WX algorithm. So we first perform some initializations and make a copy Q of P. And then we enter a while loop. While set Q is not empty, we first pick a point Z with the minimum dist value from set Q. And then we have two update subroutines. We first update the dist values of points in the cell of Z, which is the small red square, by using the dist values of points lying in the patch of Z, which points in this big blue square. And then we go back. We update the points. We update the dist value of points in this big blue square by using the dist values of points lying in the small red square. And then finally, we remove points of in this small red square. We remove these points from set Q until we perform all of these operations until set Q is empty. And then the dist values are the shortest at the lengths of the shortest passes from point S to all other points. In the first update, we need to find a point QV in this red circle for each red point V in this small red square, such that this formula is minimized. If we assign weight of dist U to each point, to each blue point in this big blue square, which is the patch of Z, then we have a key observation that the weighted nearest neighbor of each red point in this big blue square must lie in this red circle. So we can finish the first update by building an additively weighted Venn diagram on vertices in this big blue square. This can be done in n-log time. And in the second update, the key observation doesn't hold. But we have another observation that this big red square had a constant number of cells. So we can perform the update subroutine for each cell in this big red square. And so we have two cases. In the first case, the cell being updated is also the cell containing point Z. Since the distance between any 2 points in each cell is at most R, so this case can be done by building an additively weighted Venn diagram on vertices in this small blue cell. And the second case is a little bit difficult, but we have that the cell being updated and the cell containing point Z are separated by an axis parallel line. So we can perform the second update by this procedure. The first step is sorting all the points of U, which is these blue points, by the dist values in an increasing order. And then the second step is to compute a group of subsets from set U, which is these red points. So for each red point V, we need to find the smallest index IV, such that V is within the unit disk centered at the point UIV. And then V is assigned to the subset of V with the index IV. This can be done in k-log k time, where k is the total number of points inside U and V. So we get an example. In this example, V1 and V2 are within the unit disk centered at U1. So V1 and V2 are in the subset of V1. And V2, V3, and V4 are within the unit disk centered at point U2. But V2 is already in the subset capital V1. So capital V2 only contains points V3 and V4. Similarly, we have the capital V3 contains points V5. Then this part can be viewed as another problem called offline insertion only additively weighted nearest neighbor problem. We will be given a sequence of insertions, which are these blue points, and we need to answer a group of queries, which is to query the weighted nearest neighbor for each red point from these blue points. This can be done in k-log square k time. Next is our parametric search. So the first step is to building the grid. We need to shrink the interval R1, R2 to R1 prime, R2 prime, such that if R star doesn't equal R2 prime, then the grid with respect to parameter R, where R is in the shrunk interval, has the same combinatorial structure as the grid with respect to parameter R star. So this can be done in n-log cubic time by using the sorted matrix searching technique with our decision algorithm. And then we consider the rest of the WX algorithm. We notice that only one step of the second update needs to be parameterized, which is computing a group of subsets of V. So the target, we first let IV of R denote the index of the subset of V that contains point V when the WX algorithm runs on parameter R. Then the target of this step is to shrink the interval such that if R star doesn't equal R2 prime, then for any red point V and any parameter R in the shrunk interval, IV of R equals IV of R star. And other steps are independent of parameter R, so we can just proceed and follow the original WX algorithm. Next is our divide and conquer procedure to solve the parametric search of computing a group of subsets of V. We have an observation that for any blue point V in the capital V, if the unit disk centered point Uj contains V, then IV of R is less than or equal to J. While Uj are already sorted by the increasing dist values. And then we partition the set U. Let U1 be the set of the first half points of U. And then in this example is U1, U2, and U3. And then we compute the upper envelope of disk centered at the point of U1 with radius of R above line L, which is the red curve in this example. And then we shrink the interval R1, R2 to R1 prime, R2 prime, such that if R star doesn't equal R2 prime, then for any point V and any parameter R in the shrunk interval, V is below this upper envelope. If and only if V is below the upper envelope with respect to parameter R, if and only if V is below this upper envelope with respect to parameter R star. This can be done in n-log cubic time by a procedure in a previous work proposed by Wang and Zhao in 2021. And then let V1 denote the set of points in V that are below this upper envelope. This example is V4 and V7. And then for any point V in V1, the IV of R is equal to IV of R star and is less than or equal to the cardinality of U divided by 2. And for any point V that is not in V1, IV of R is equal to IV of R star and is larger than the cardinality of U divided by 2. So we can recursively solve the next two instances. The first one is defined for U1 and V1, and the second one is defined for the rest of the red point and blue points. Until the base case is given, which the number of red points is only is 1, and the base case can be easily solved. One level of recursion can be done in a total of n log cubic n time. So all the levels of the recursion can be done in n log to the first n time. And suppose the destination point T is within a cell of Z in an iteration, then R star is equal to R2 after this iteration. This can be done so the destination point T can be reached in order of n iterations, and this could cause a running time of n squared. So we need to improve this result. The first step is building a grid as before, but next we need to classify the cells of the grid as two types, the large cell and the small cell. The threshold n to the 3 over 4 times log to the 3 over 2n is carefully chosen to balance the running time. And next we pre-process all small cells, restrict the interval such that if R star isn't equal to R2 prime, then for any 2 points UV lying in a pair of neighboring cells, neighboring small cells, an edge connects U and V in UNEJ graph with respect to parameter R. R is in the shrunk interval if and only if an edge connects U and V in the UNEJ graph with respect to the best parameter R star. So since each small cell contains at most this number of points, so the preprocessing can be done by using a subroutine of the distance selection algorithm proposed by Catherine Sharia in 1997 with our Desirian algorithm in n to the 5 over 4 times log to the 5 over 2n time. And then we enter the main loop. We need the main loop of parameterizing the WX algorithm. For each pair of cells in second update of an iteration, if both involved cells are small cells, we know the connections between points in neighboring small cells after the preprocessing of the small cells. So we can just run the original WX algorithm. So the total running time for this case is n log square n. And if at least one involved cell is a large cell, we just apply the parametric search. The number of large cells is at most n to the 1 over 4 over log to the 3 over 2 log to the 3 over 2n, and each pair can be solved in n times log to the 4th n time. So this case costs a total of n to the 5 over 4 times log to the 5 over 2n time. This is the same as the running time of our preprocessing for all small cells. So the total running time for our L2 weighted case, for our L2 weighted RSP algorithm is also n to the 5 over 4 times log 5 over 2n time. Okay, thank you very much. Okay, so do you have any questions?
Okay, please feel free to ask question to Yami. We'll be answering. Okay, if no question, please. Okay, I have one question. Okay, so you have actually considered L1 metric as well as L2 metric, right? For this problem.
Yeah.
So how about L infinity metric? So is there any result known for L infinity metric? Means if you don't have disk instead of disk, if you have hypercubes or maybe some squares, right? Then so did anybody study that problem?
So you mean the L infinity metric, right?
Right.
Yeah, so I think the L1, our algorithm for the L1 metric can be used to the L infinity metric with some minor modifications. Yeah.
And how about, let's say, instead of you need this any object, let's say I will take some convex object, right? And all of the other objects are translated copy of them. Then also is there some known result or something? And how about the lower bound of this problem?
Oh, I'm sorry. Could you say again? What kind of different objects?
So let's say some object is given. It might be any convex object, and other objects are just translated copy of them. So instead of unit ball, right? So unit is different.
Yeah. Well, we didn't consider some other objects like square or ball, because for unit balls, so our efficient algorithms mostly based on the Voronoi diagram, which is a structure for the nearest query in 2D plane. But for unit balls, we don't have some structure similar to the Voronoi diagram in 2D plane. And for the square, we haven't considered them. I think that is more difficult than the unit disks, because for the unit square, you also don't have some efficient structure to query the nearest neighbor. Yeah, I think that is a key problem.
Okay, I have another final question, maybe. So, so for the unit disk graph, right? You have studied this, so and you have improved the result, right? So the question is, how far you can improve? Is there any lower bound known, or people have studied that with respect to
we haven't proved the lower bound, but I think maybe n log to n times polynomial factor with log n. I mean n times yeah. So now is like our result is n to the 504. I think the best result may be like this: n with polynomial factor of log n.
So, does anybody has any question? Please feel free to ask. Okay, if no more question, let us thank the speaker once again. And
thank you so much.
Thank you. So let us also thank all the speakers of this session, Shujo, Rebecca, and Ewing. Okay, I think this is the last session of today's WALCOM day, right? First day, and with this I am just giving this to the local organizer to say something, or maybe we can conclude today's session. Thank you.
Okay, thanks to Mrs. Minade. Okay, we would like to thank all the chairs and presenters in the contributor talk session. On behalf of the committee, we apologize if there are mistakes. See you tomorrow at 9 o'clock. Okay, thank you.